Good morning. Welcome to the Apple Disco Party talk. If you like macOS or file system vulnerabilities, you are at the right place. My name is Csaba Fitzl. I'm working at Kandji as a principal macOS security researcher. I used to work for OffSec, writing a macOS exploitation training there. Even before that, I used to be a red and blue teamer. And I do a lot of macOS bug hunting. I'm close to 100 CVs now, married, have 2 kids, and I'm really into trail running. The agenda, there is a lot to cover, so it will be a quite fast-paced talk. So first of all, I will talk about the disk arbitration service, what it is, why it's good for us or interesting. And then I will just cover 7 different vulnerabilities, most of them associated with this service. So let's start. What is the disk arbitration service? It's a system-wide service on macOS defined in the COM-Apple disk arbitration plist. And it does offer a MAC service globally under the same name. MAC service is basically a service which can be reached over MAC inter-process communication from other processes. And the main role for this service is basically managing disk mounting and unmounting. You can also use this service to register a callback for mounting, and then you can approve or reject these operations for the user. But eventually, this service will call the mount and unmount commands, binaries under the hood, to perform its operation. But the idea is that it basically masks the difficulties of the mount operation from you. But why we like it as security researchers? So first of all, it runs as root, so it's quite a privileged process. It runs unsandboxed, so it's also good. It kind of has full disk access rights, which comes through the COM-Apple private security storage exempt heritable entitlement. Full disk access is basically a very wide privacy privilege on macOS that you can access basically all of the user private data. And the MAC service it offers is reachable from the application Sandbox. So basically, we can potentially also use it to escape the Sandbox because we can reach it from there. And additionally, it's also open source. So it's one of the open source packages from Apple. So it's easier to audit the code base of this service than other closed source ones. So actually, the MAC service it runs, it's actually running on top of Mac and not XPC, which is more widely used nowadays on macOS. And the Mac interface is generated by MIG, the Mac interface generator, which basically simplifies the interface. But we don't even need to deal with that because there is a public disk arbitration framework where there is a function for every single MIG routine, and we can just call them. So this is a basic call flow of the mount operation. So when disk arbitration receives a request to mount something, this is the call flow it will go through. So every single request, not just for mount, but also unmounting and everything else, will arrive in the DA server session queue request. This is probably the most important function in the entire daemon. It will do all the permissions check for privilege, for sandbox. It will also perform authorizations and so on. This is very important because if like an unprivileged application calls this service, it needs to ensure that it conforms with the other application rights to basically to prevent privilege escalations or sandbox escapes. Once it's done with all the checks, it will go through a bunch of internal functions, eventually arrive to the DA file system mount with arguments, where it will build up the external mount command options. And eventually, it will call DA command execute, which will call POSIX spawn, and it will just run mount command with a bunch of options. So with that, let's jump into the vulnerabilities. So the first one is a sandbox escape. This output was taken from another exploit, the end result of an exploit, where I dropped a DMG file, like a disk image, from a sandbox and mounted it with diskarbitrationd. Now, there is a problem with this mount, which I didn't spot at that time. And the main problem is that the quarantine flag is missing from this mount point. Why it's a problem? Because if there is no quarantine extended attribute, the files will not be quarantined on the mounted file system. If the files are not quarantined on the mounted file system, then there will be no gatekeeper checks on the applications we try to run. Technically, there is a gatekeeper check, but it will only ensure that the code signature is valid for the application, but it will not check like notarization, approved developers, and so on. So basically, we can just run any application we want from that image. And if we can launch any application, it means we can launch like an unsandbox application and then escape the sandbox. So if we can manage to mount a disk image without the quarantine flag, we can use it for sandbox escape. Now, what was the actual issue here? Like, beyond the quarantine flag missing, why it was missing? So obviously, diskarbitrationd didn't add the flag during the mounting, which was weird at first sight, because in diskarbitrationd, there is actually a function which will query the I/O registry for the disk device if the device has the quarantine flag set, and the device did have the quarantine flag set to yes, yet diskarbitrationd didn't apply the quarantine flag for the mounted file system. So I was wondering why it's happening, and it turned out there are two call flows. There were two call flows inside diskarbitrationd. The first one is when we call open command on a disk image, or when we double-click on that image. In that case, it will call disk create from IO media, which call the IO registry search, and we look up the quarantine flag. But if we already have a disk image, sorry, not a disk image, but like a dev device, which is a result of a mounted disk image, and if we try to mount that device, even if it has the quarantine flag, there will be no check. So if we just call disk create from BSD name, like dev disk, and it will just call the mount operation without that flag. So let's say we are in the sandbox. How can we get a dev disk device on the system? Because a DMG file is not a dev disk device. And to create a disk device, that's done by the disk management daemon, which is not reachable from the sandbox. But the trick we can do is that we drop a DMG on the file system, and we run open DMG. That will result the system opening the DMG, creating the dev device, and mounting it in a default location. Now, at that moment, the dev disk device will be created, and it will be also mounted, which we don't want because, first, in this case, it will have the quarantine flag set. Two, we want to mount it somewhere else. Luckily, from the sandbox, we can unmount this disk using the diskarbitrationd API, and then just remount it using the other function with diskarbitrationd. So basically, that's how we get a disk device and can play with that later. How Apple fixed it? Basically, they moved the quarantine flag assignment down to the kernel, and this IO registry lookup will happen every time we try to mount a file system, and the kernel will enforce the quarantine flag on the file system. Now, before we go into the other vulnerabilities, I want to go through a couple of call flows, because these will be more and more complicated as we go, and we need to understand the basics. So mount only call. We have a caller, like our application which runs as the user, root, whatever, might be Sandbox, and it calls the mount command. In that case, the mount command will run with the same privileges as the caller. The mount command will call into the kernel through the mount system call, and the kernel will check the classic POSIX permissions, like if the user have privileges over the directory they want to mount, and it will also do the the mandatory access control framework callouts for Sandbox verifications, and so on. So let's see an example. I'm the user, try to mount over a directory which is owned by root, and the disk owner is asked root. The disk ownership will be important later, so I just keep it being listed. I call the mount command, it will run again as user, and when it hits the kernel, it will fail because the user doesn't have privileges over the root-owned directory. Now, let's see how the mount operation happens when we have diskarbitrationd in the pipeline. So now we have the caller, again, running as X with some privileges, which calls into the diskarbitrationd. Now, that runs as root and unsandbox, and it will do two checks. One, a sandbox check. Two, it will check if the calling user ID is the same as the disk owner ID. This is because it will call the mount command with the disk owner privileges. And then the mount command, again, calls into the kernel. So again, let's see an example for this. I'm the user, want to mount over a directory which is owned by root, and the disk owner is also root. Once I get to diskarbitrationd, that will fail because the user is not the same as root. Again, the disk ownership is being checked. OK, so let's try to mount a disk which is owned by the user, again, over a directory which is owned by root. I get to diskarbitrationd, I get a pass, it will say, OK, you can go on, and it will call the mount command with the privileges of the disk. So the mount operation privilege will be the user, and once it gets to the kernel, this will, again, fail. So this is basically how we ensure privileges in this case. So let's see another example. Try to attack diskarbitrationd with a symbolic link, which was possible in the past, but now it's fixed. So let's say I'm the user, and I have a symbolic link pointing to temp mnt. That directory is owned by the user. The disk owner is the user. Everyone is the user. We just have a symbolic link. Gets to diskarbitrationd, pass, privileges, all fine. It will call mount. But I didn't say before that the mount will have the -k options, which means it tells the kernel to not follow any symbolic link in the entire path of the target. So it will call into the kernel, and basically it will fail because there is a symbolic link on the target. So although privilege-wise this would work, but because of having a symlink in the actual operation, this will fail. And actually, this is a very, very, very important step in mitigation. So with that, let's go to the second CV, which was both a sandbox escape and a local privilege escalation on diskarbitrationd. So diskarbitrationd supports two types of file system. One, which is backed by kernel extension, which are like kernel drivers, and ones which are backed by user-based file systems, so like user drivers. Now, the problem is the symlink check is not enforced on UserFS mount. So here on the source code on the right, we can see that in case of UserFS, when diskarbitrationd put together the mount command options, the -k was missing. So this was the first problem. Second problem was that diskarbitrationd called into fskitd, which was running as root, and fskitd called the mount command as root every single time, regardless of the disk owner or the caller, user ID, whatever. So it was running as root, and no symlink check enforcement were happening. Again, this is just a summary of what I just described. So how we could exploit this? I'm the user. I created a mount point called link and pointed to like a place which is OK from privilege perspective. I call into diskarbitrationd, it passes the check. Diskarbitrationd calls into fskitd, and at that moment, I will swap the link to a place which is like not OK, which is maybe owned by root, or allows me to escape the sandbox, and so on. fskitd, we're calling the mount command as root, so it's running as root, and I still have the link. And because there is no -k option, the kernel will not care and just follow the symbolic link for the mount. So how we can weaponize this mount attack? Because what we achieve here is we can mount a disk over a directory as root, but how we actually get code execution as root? Apple is very good in locking down weaponization methods, so many of the default ideas are now protected by TCC, the privacy daemon, so you cannot mount over many directories. But one which is still open, and I guess it will be closed soon, is mounting over the etc cups directory. So we mount over the etc cups directory. The cups is the Unix printing service. And we drop a cupsfiles.conf file. And in this file, we set the error log option to etc sudoers.d/lpe or any file. And we can also set the log file permission to 777, which means that anyone can modify and write this file. And we also add some junk to the configuration file in order to actually trigger an error logging. So this file will be created with 777 permissions. Then we call cupctl, which will trigger the cups daemon, and this file will be created. At that point, we have the sudoers DLP file created with 77 permissions, and we can edit it, and we will add the staff all, no passwords, all line, which basically means anyone can run sudo without providing a password. And everyone will be elevated to root without a password. But because the permissions are so wide, sudo will ignore this configuration file at this point. So what we need to do is, again, change the cupsfiles.conf file and now set the log file permission to 700, which means only the root can edit and read this configuration file. We call cupctl again. Again, it will produce some error logs, and it will reset the file permissions. And then we can call sudo su. Although there will be some junk lines in this file, sudo is just nice enough to ignore all of these. OK, so this was for privilege escalation. How we can actually utilize a mount operation for escaping the sandbox. So one idea is to mount over the library preferences directory, which stores all sorts of configuration for many applications, and drop a terminal configuration file. And in terminal, we can set a command string configuration, which is basically a shell command which will be executed upon opening terminal. Now, terminal runs on Sandbox, so whatever we put here will be run on Sandbox. The command I put in is basically a link to the shell script, which will be in the same directory. And this shell script will achieve the previously described LPE. So here is a demo showing this. So I open terminal. I show that I'm a low privilege user, and I have an application which is sandboxed, the DA user. And I cannot do sudo su. It asks for password, and nothing interesting is mounted at this stage. And now I start the app, and it drops the DMG with the open command. Again, we need a device, unmounts it, and now starts the race condition attack. We escape the sandbox. We open terminal, and now it's running the LPE script. It takes some time because cupctl is a bit slow to trigger. So we need to wait always 10 seconds, approximately 10 seconds to ensure that the files are created, like the error log file is created, permission set, and everything. We already mounted our etc cups, trigger cupctl for the first. Waiting a bit, yeah. And that's it. Now we are root and on Sandbox because it's all in terminal. So how Apple fixed this? Now the nofollow option, the -k, is basically enforced on every mount, including UserFS file system, and the fskitd now gets the original requestor ID and will execute the mount command with that user. OK. The next one was the Sandbox escape and the TCC bypass using directory traversal. So again, we have the same setup with diskarbitrationd. OK, my screen is changing a bit slow here. So what happens is when we call into diskarbitrationd using the diskarbitration API, there is a da-disk mount with arguments common function which uses the real path and the CF URL create from file system presentation APIs to basically resolve the path, which will resolve any symbolic links. Obviously, we can change that later. And it will also remove any .. in the path. So when I call into diskarbitrationd, I cannot basically pass a .. because it will be removed at the framework. Inside diskarbitrationd, when it does all the privilege checks and the sandbox check, it will also do some resolutions, but only for the time of verification. That resolution is not permanent, so that resolution is not passed to the kernel. But eventually, the kernel will do all the final resolutions. But the important thing here is that the path we pass to diskarbitrationd is unchanged, basically, from the moment it leaves us till it gets to the kernel. And if you have a symlink there, it will basically fail at the kernel. But because this API is happening on our side, on the caller side, we have control over that. And what we can do is retain any .. We don't have to call the provided API. We can re-implement it ourselves, especially that it's open source. It's pretty easy, so we can just copy the function, remove the real path resolution and the other resolution, and just pass the same call, and then .. will remain in the call. So let's see how we can exploit this. So we set the target to private temp dir .. users, etc. com Apple TCC. Com Apple TCC is the directory where the TCC database is stored with all the privacy privileges set for the user, basically. And we also have a symbolic link on dir pointing to private temp 123. We send it to diskarbitrationd. When it will call sandbox check would ensure that I cannot mount over com Apple TCC. It will resolve this path for the time of check, and it will give a pass because the resolution is private temp users, etc. That's not in the user's home directory. It's fine to mount over this directory. Now the mount command is passed, and we delete the symbolic link and replace it with a regular directory. And when it hits the kernel, again, we don't have a symlink anymore, so it will not fail. And the private temp dir, etc. resolution will be users, crab, library, application support, com Apple TCC, which will got a pass. And here's a quick video showing this. So we have, again, an application which is Sandbox. We can see that there are no permissions for files and folders in TCC. And just to ensure, I also don't have anything mounted here. And now we start the Sandbox application. And it's done. So it could run commands from the terminal, which is on Sandbox. And now we can see that terminal has some extra privacy preferences. It can access the desktop documents downloads folder. So however, fixed it. Now there is no resolution happening on the caller side at all. All that resolution was moved into the diskarbitrationd daemon, which is good. But there is more to this. Actually, there are two call flows now inside diskarbitrationd. It will check if the dailies mount option no follow option is set on the mount operation. And if not set, it will resolve the pass and then do everything normally. Now, you could think that, OK, if we set this option, then no resolution is happening, so we could retain the .. pass items, which is true. However, the Sandbox check also got an update, and basically it will disallow any symbolic links and .. in the pass. The reason Apple had to do these two call flows, we will understand from the next exploits. So the next one is an LPE through StorageKit. We have some new players here to complicate the call flow. Now, instead of calling into diskarbitrationd directly, we can call diskutil. Diskutil can also mount disk images. But diskutil, instead of calling diskarbitrationd, it calls into storagekitd. Storagekitd calls into diskarbitrationd, and so on. Now, StorageKit runs as root and on Sandbox, and it also have kind of full disk access permissions. And it does a Sandbox check, but it never did a privilege check. And it's a problem because from diskarbitrationd point of view, the caller is not us or diskutil, is storagekitd who runs as root. So what happens? My screen, again, a bit late with that. So we have the operation. We are the user. We want to mount over a directory which is owned by root, and the disk owner is also root. That's like a local APFS volume. We call diskutil. It runs as the user. Again, we call into storagekitd. We got a pass because there is no privilege check happening here. StorageKitd, we call into diskarbitrationd, but now the privilege, like the caller privilege, is root because StorageKitd runs as root. And now what diskarbitrationd compares is the privilege, root, and the disk owner, which is also root, and they are equal, so it will get we will get a pass. And it will call mount as root because the disk owner is root. Everything is root. The kernel will just say, OK, you can mount it. So basically, we can trivial mount with diskutil any any disk which is owned by root over any directory which is owned by root. So we can play the same privilege escalation trick with etc cups. There is not even a race condition here. So if we run this, we create a new APFS volume. You can do that as the user. And again, we mount it over etc cups, and we just need to wait for the trigger twice, 10 seconds, and then it's done. Yeah. You can see the error messages printed by sudo, but again, sudo doesn't really care. OK, so Apple fixed this. Unfortunately, it wasn't good at first, so we could utilize this, it again for privilege escalation, but now also for TCC bypass. So what happens is inside StorageKitd, now they added a privilege check. But if you recall, when we call diskarbitrationd through the diskarbitrationd API, there will be a path resolution. So what we can do is play a symlink attack with alternating a symlink. So when we call, and we can play the same trick not only with the privilege check, but also with the sandbox check. So what happens is we are the user, and we want to mount temp link. When it gets to storagekitd, we point that link to temp mnt, and that's owned by the user. The privilege is user. So storagekitd will say, OK, you got a pass. We quickly swap the symbolic link, and storagekitd will resolve it again when it calls out to diskarbitrationd. And at that point, it will point to etc cups, where the owner is root. But now the privilege is root. And again, all the privilege checks by diskarbitrationd and the kernel will get a pass. So basically, we could raise the privilege check inside storagekitd. I will skip this video because time is running. So this is why this fix was needed. Whenever storage, so let's say we have a normal user. We follow the normal call flow. So we get to diskarbitrationd, there will be a path resolution, and everything will go as normal. But when the request is coming from storagekitd, there shouldn't be a path resolution happening, because if there was a path resolution happening, it would mean that we could play the same race condition. So it's really, really important that when the request comes in from storagekitd, the path is retained as it was checked by storagekitd. So storagekitd will set this DA disk mount option no follow option, and then there will be no path resolution. And if there is a .. or symlink in the path, then the sandbox check will drop the request. OK, so this was diskarbitrationd and storagekitd, but there are two more lightweight items. The first one is bypassing time machine data protection with APFS. So time machine backups are protected by TCC, the privacy framework on Apple. This is because time machine backups by default contain all of your private data, desktop documents, contacts, messages, everything. So it's very important that attackers cannot access this data. And if you have full disk access permissions, then you can access time machine. But if you have full disk access permissions, you can also access any other file as well. So that's fine. Now, the way the time machine backup disk is set, there are APFS disk roles defined by the APFS file system. And one of the roles is backup time machine role. And if we list the volume disk role for our time machine backup, we can see that it has the backup role. Also, if we check the Sandbox platform profile, this is like a decompiled subset of the Sandbox profile. We can see that there is like a file attribute, time machine device, or time machine backup. It will assign it to the time machine storage class, which means that it will be protected by, basically, by TCC. But what we could do is we could change the volume. We could clear the backup role from this volume. So once we cleared it, then we unmount the disk, we remount the disk, and because it doesn't have the backup role anymore, we can just access all the files on the drive and basically get access to all of the user private data. The fix was that we can no longer change or clear APFS disk roles. And the last one is disk utility privilege escalation. ASR is a command line utility in macOS. It's the Apple software restore utility, and it's used to basically restore disk images or disk on the device. This is like a bit copy restore. So we can take a DMG, a disk image file, and restore it to the volume, or take one volume and restore it to the other volume. If we call it from the command line, we have to call it as root, otherwise it will not run. But we can also call ASR as an XPC service, so through IPC communication, through the COM-Apple ASR service handle. But to reach it through XPC, we have to have the COM-Apple private ASR entitlement. Now, this entitlement is disk utility, the GUI utility does have this entitlement, but you cannot assign this entitlement to yourself because it's a private entitlement. But because this utility has it, we can use disk utility to restore a DMG file which has a SUID binary embedded inside. We can prepare this DMG offline. And because this utility doesn't ask for the password, we can use the GUI to basically drop a SUID file on the system, run it, and get root shell. Now, this is like a GUI-heavy exploit, so we need GUI access for this. So it's kind of limited use, but let's say you have an unattended workstation in an enterprise, then it's a good way to escalate privileges to root from that user if you don't know the password. So this is how it works. In this utility, we just create a new volume. And into that volume, we say we restore it, and we restore it from our disk image. This disk image has a SUID binary. Restore is done. And now we can go to terminal, and we can see we cannot run sudo, but we have a SUID binary on this newly mounted volume. Restored volume. We can run it, and now we are root. Conclusion, well, diskarbitrationd has a very long history of vulnerabilities. This is just the new ones I found in the last 1 year. But it's a daemon that keeps giving. So that's all. I still have 2 minutes. If there are any questions, we have 2 minutes for that, or you can find me after the talk. Thank you. There is a question. Sorry, can you come to the microphone so everyone hears it?
So it seems like this notion of the privileges of disks, whether it's through cups or through restore, is kind of an inherent problem with the system and not something that's just popped up once. It seems like something that continues to be an issue in system design. Do you think it might be possible to apply some kind of formal methods or model checking approach to demonstrate that the way that these permissions are set up doesn't have issues? Or how do you think we can create a system that's more resilient so we don't have this continue to come back over and over?
I think the problem is not with the actual ownership of the disk images, because if you are a user and just open a DMG, that will be owned by the user and not the system. It's basically, I think it's very hard to handle these call flows when you want to mount something and you need to cross several daemons to do something. And you need to ensure that you check everything at every single component. And if there is error in any point of time, basically you have a problem.
So if I'm designing a system that has different permissions and all these layers of complexity, is there some advice that you would give to avoid introducing these kinds of problems? Or if I already have a system, is there some way that you can, I don't know, have some guarantee that these things won't arise in the future?
I don't know, but I do think this is a hard engineering problem to solve. Even when I submitted some of these vulnerabilities, I actually literally had to think myself, how would I fix this across multiple components? I think there should be like, not just like, let's say Apple has one person developing diskarbitrationd and another person developing storagekitd. There should be someone or some engineering team overseeing the entire process and engineering the entire code flow across end-to-end, basically, and probably not just here, but if there are other similar places, then there as well.
Thank you.
Thank you. Sorry, we are out of time, but if you have questions, you can find me here. Thank you.